So I talked about this already back in July, I think, but Albert Stebbins was interested and said that he could see a way of constraining this idea, this topology, with periodic boundary conditions. And he's going to talk about that. I hope he comes later in this meeting. But I thought I would remind people about the topology that I'm talking about so that you have it in your head, because I think it's difficult maybe to conceive of this. So this is a topology of the universe. Okay, there's an idea for that. And based on the two hypotheses. One is that there are no boundaries to space-time, and the other is that there are no infinities in the physical world. Infinities have their place in mathematics, but not in physics. Okay, that's the hypothesis anyway. And from that, I conclude, suggest a particular topology for our universe. Okay, and so let's start here with just starting right at the beginning with just one space dimension and one time dimension. So space to start with here. Hi Albert. I'm just starting with my cartoon introduction here.
Okay.
So this is a plane of boundaries. This is one dimension of space, just a line. That's all there is for space. But one dimension of time. And you can see that this particular space-time model of our universe, one line in space, is finite and bounded. A particle will travel on a path in this plane called a world line, and it's constrained to be not going faster than the speed of light, which is constrained on the angle in this plane. And I put here two other dashed line coordinates called z prime and t prime, because as we know, as Einstein taught us in special relativity, the space and time actually get mixed up, and you can, with a different speed of a particle, two particles with different speeds have different rotated axes in space and time. So for a particular speed particle, the time-primed axis would be shifted to the z-primed axis too. So, but some things are constant, like the absolute, I'm not going to give a course on relativity, but I don't want to mess with special relativity. Let's keep that. It says that z and t get mixed up when motions are taken into account. And there's this equation, these equations here, that relates the time in one frame, t prime, to the time in another frame, t, by the speed of the particle. Actually, that should be speed rather than v is speed, actually. An exponent like this. So this mixing up of space and time in relativity actually suggests, I think later, that if space is bounded, which I'll come to, then it's natural that time might also be bounded. Now, okay, so this space has edges here. In this particular simple plane, the particle gets to here, and it's got to the edge of time. Or a particle gets to here, it's got the edge of space. So there's an edge of space in this case. It's one line moving in time. But we can eliminate these boundaries, endpoints of space, edges of space, endpoints of time, which have conceptual problems. And we can eliminate them by wrapping around. Why am I going there? Okay. So let's say take that plane, wrap space into a cylinder. So you've joined one edge with the other edge. You have no edges left. Space is continuous, no bounds, but finite. Space is the outside surface of the cylinder. It's now still one-dimensional, and time is this way. Time still has a beginning and an end in this picture, but you can then wrap time into a torus by wrapping this much into a garden hose, and you join the two ends together, and you get a torus like this. You join TA and TB, so now time is finite also, and has no boundaries. So there are no boundaries in space or time. The whole physical universe, still one space dimension, is on the surface of this torus, right? And in this representation, space and time are orthogonal, which is not unnatural to us when we do space-time diagrams of relativity. And of course, in space, special relativity, t and x-axis can be rotated by us, but that is just a side remark there. So that there's now that's just a one-dimensional universe, one of space and one of time. So let's now graduate from one space dimension to two space dimensions. I'm going to call them x. I actually call it x and y. I call it x and y here. And I'm showing the two space dimensions as the surface of the sphere, like the Earth. Of course, this is just one coordinate system here. In fact, all the points on the surface are absolutely equivalent. There isn't a pole. I mean, it's just a spherical surface. And then it's getting harder to show time, but let's add the time dimension, and we show that surface moving through time. So the surface now, it's two-dimensional, it's got no boundaries, and it's finite, but it's moving through time. And I previously eliminated the boundaries of time by making time closed loop as before, and now you get this picture here. Somehow it's just representing that as time goes around the loop, it's got no beginning, no end, it's finite, no boundaries. Then you have this two-dimensional space, the surface of this sphere. Forget about the inside of the sphere, just the surface. And then I went one further step and constricted the size, and made the size time dependent, constricting the size at one point around the ring here to be very small. Could be the size of a proton or something. I don't say it's a singularity, because a singularity implies 1 over infinity, which is by hypothesis thrown out. So I have and this very small point here, I couldn't draw it of course, but I call it BCB, Big Bang, Big Crunch, Big Bang, which is a singular point on the loop. And that's now for a two-dimensional universe.
Can I ask a question? Why do you think that two space dimensions forming a sphere and not a torus again? I mean, usually it's a more regular manifold for two-dimensional motion. It's a torus. Sphere
it is a torus, actually. I just can't draw it as a torus like this.
Oh, okay.
It is a torus.
So I mean, usually it's not S2. It's a T2. Usually.
This itself is S2, but when I put it into add time.
But why is it S2 and not a torus? Why don't you use sphere?
I think it's arbitrary.
I'm sorry?
I think it's probably arbitrary. Could be the one.
This is a torus with two space dimensions and one time dimension.
Okay.
But it's not right to, let's see if I get.
I mean, a sphere is just some partial case of torus, I guess.
Right. It's not right.
No, it's not the same.
I mean, it's only the surface of this torus. This is a one-dimensional space, one-dimensional time. Right? And it's only the surface that has any physical validity. And now I'm turning this one-dimensional space into two, in spherical form, topologically speaking. And and this is a way I can sort of draw it. So this is a two-dimensional universe. It's the surface of a sphere, and it grows and gets to a maximum size and then crunches down again. But I still haven't got three space dimensions. It's getting harder to draw it. But before I get to three space dimensions, let me describe a simple way to see how two surfaces finite but unbounded. Of course, you see at the surface of the Earth, it's finite but unbounded. But suppose you start at the pole, or anywhere on the Earth. You start here and you've got a very large supply of paint, and you start painting a circle, an increasing spiral around yourself. The outer rim of the spiral is getting bigger and bigger, and the curvature is getting less and less as it gets bigger and bigger. And eventually, at some point, you've covered half of the sphere. And then the boundary is a straight line. You're going along the equation as far as you can see. Keep painting, keep painting, keep painting. And then you start to see that the edge of your paint is now concave. You're getting more and more smaller and smaller radius, and eventually you find yourself at the opposite pole, and you've painted the whole surface of the Earth, and you're standing on the last remaining unpainted bit. Okay. Now I say that, which is pretty obvious, but now let's go to three space dimensions, which is what we live in. So to do the same trick there, the same Gedanken experiment, you start with a ball and you start wrapping tape around it. You've got a huge supply of tape, you make it bigger and bigger, and eventually the surface of the ball that you're wrapping tape over appears to be flat to you. Keep going, keep wrapping. and it starts to see concave, and then the radius gets smaller and smaller, and eventually you find yourself in a cavity having filled the whole three-dimensional space in with tape. Okay, so now there's no boundaries to that. So that's just a sort of way of thinking about this. It's got no inside, no outside, no boundaries, a finite volume, and I can't really draw it. Nobody can draw it. I think Einstein suggested this, that space was finite with no boundary. So that's, well, he went that far. He did not, as far as I know, go an extra step and say that time also is finite with no boundary. But I've added a closed loop of time to this picture, so it's a three-dimensional closed space with one-dimensional time. That's, in my picture, the whole of space-time. And then you can constrict the spatial volume to be very small at one point, not at one place, not infinitesimal, but could be very, very small in the timeline. So this is my suggested topology of totality. That's it, it's for our universe, okay? Now there may be more dimensions on a tiny scale, like in some superstring theories and so on, where you have Calabi-Yau spaces with extra dimensions, maybe 10 or something like that. I'm ignoring that at the moment. But a point I want to make here is that although time is a closed loop, nothing happens over and over and over again ad infinitum. There's no ad infinitum. Time, the whole of time is there in that closed loop. Now I think actually that it is probably required, but maybe Albrow can say more about this, that the closed loop that I'm talking about does have a constriction at some place, because if it was not expanding or contracting, if it was just a big fixed finite size, then I worry about entropy, because entropy is increasing all the time. And so how can it be that a point in the far future is identified with a point in the far past? But if you have this big crunch, big bang, then I can see a way, I think, in which, although the entropy is increasing as we see the universe expanding, when it comes down to a big crunch, you can still match this boundary condition that maybe Albrow talked about, and still match the universe beginning. Now, there's one final thing I would okay, out of order, but what about consequence? I showed this slide last time. These two hypotheses. So various consequences. Is it physics or philosophy or what? Can you prove this is wrong? Now, one consequence is that the apparent accelerated expansion of the universe, that's dark energy, if it really is an expansion of the universe, accelerated, be temporary, because otherwise you have forever future, infinite future, and I don't have. So this would make a prediction, if you like, that eventually, in the far future, the universe will collapse. But of course, it's hard to test that without letting take the end years. But maybe it's possible that this apparent accelerated expansion is relatively local, and that far, far away, it's not doing that. So like a balloon with points coming out there. The universe is closed, but perhaps only just closed. So omega would be, I think it's 1 minus epsilon, right, Albert?
Yeah.
Closed, but only just closed because. So
it's for close. It's 1 plus epsilon. If epsilon's positive.
Okay.
Can you explain what does it mean? This omega equal 1 minus epsilon.
Cosmology.
Well, there's something called the density parameter, which is omega, which is basically the energy density divided by the square of the Hubble constant times some factor.
Oh, okay.
And if that's equal to 1, it's sort of on the border.
1 is Euclidean space, right?
Yeah,
Omega 1 is Euclidean
one has
space.
spatial Euclidean hypersurface.
Okay.
If omega was 2, then I understand the universe would collapse in a very short time, not long enough for life to form. If it was, on the other hand, 0.1, it would have blown up much faster. So But it's not exactly one because that would be flat, and my space-time is not flat, it's curved, it's romantic. Total energy of the universe is 0. Now, space is closed, so no lines of gravitational force, if you like, can escape and go out, or lines of electromagnetic force. So the charge is 0 too. And this implies that if you have two stable charged particles like protons and electrons, the numbers must be 0. So by the total energy of the universe being 0, I mean that must mean that the energy in matter is exactly compensated by negative energy, potential energy, whatever one want to call it. Now, the other thing is that the baryogenesis, which we see the universe as we know is all matter, so what happened to the antimatter? And the standard answer is that at the very beginning of the Big Bang, it was symmetric, but then a slight asymmetry caused most of the matter and antimatter to annihilate, leaving just a little bit of matter left over. But in this case, there is a possible different picture, which is that if you zoom in on this place where you have this big crunch Big Bang event, where the universe became very, very small and then grew again, if you look at that just part of the universe, then it looks like pair creation of the universe anti-universe. You have world lines coming in on one side and going out on the other. So that, if you like, if you just focus on the beginning, Big Bang, and so on, which may have been CPT symmetric, that timelines appear to be coming in, and then so that is one way of seeing how we could be all matter without having a great annihilation event. And then the photon-to-baryon ratio in the universe should be explainable without such an event. You don't have to have this great annihilation of nearly all 10 to the 9, 10 to the 10 matter particles to give photons. What happened? The old question is like, what happened before the Big Bang? We kind of have a beginning and we have an end. They're moot questions. Can't fall off the edge of the earth. There's a qualitative answer to those questions. Big Bang BCBB is not a singularity. It can be very small. In fact, if there are 10 to the 80 protons in the universe, particles, you could compress them all into a size of order of Fermi without them having to, if each one is taken like a Planck volume of space and time. It cannot be a singularity in central black holes either for the same reason, because my hypothesis we don't have infinite anything. So the collapse of the black hole must stop at or above Planck scale. And I think that, well, there were theorems saying you have to have singularity, but that's not there as assumption. So that was anyway my mini review of this. I think the hardest thing to get in your head is why time is not going over and over and over again. It actually is, that's it, time, the whole time is there.
So it's like world lines in relativity.
World lines.
World lines, they are all, yes, all there.
Yeah.
So it's x, t, we are considering the entire trajectory of the particle, whatever it is, as entirely there.
Yeah.
We are not running along this line. We are seeing it all together.
Well, we're moving forward in our time. That's our psychological time.
Yes.
That's a different matter. Now,
Yes.
the psychological time is another question, which I believe is related to increase in entropy and entropic time. But that's a different.
So you consider it not from entropic time, but from objective, I would say, or how I don't know how would you like to call this time, objective time, or maybe I don't know.
Well,
No,
okay, now we are getting a bit philosophical, but my philosophy about that is that now, at our point in space and time, psychological time and time as defined by the increase of entropy are necessarily the same, and time as defined by world lines of particles, like you said, electrons going forward but positrons going backwards, and positron forward, is a sort of third way of talking about time. But now, in order to have time as a closed loop, the entropy increase that we're seeing as we smash a teacup on the floor has to go down back to 0 actually, in the Big Crunch. And the way I see that is I sort of define entropy as a number of states available for a system. So like, like take a neutron, single neutron sitting there, a single state, entropy is 0. But as soon as it decayed into a proton, electron, neutrino, there's a large number of possible final states, so the entropy is jumped. And that jump occurs. Now, in the Big Crunch, the densities, all the particles in the universe are coming down. You can have conservation of baryon numbers, so 10 to the 80 particles coming down to a very, very small one. And then the reverse reactions, like electron, neutrino, and proton coming together, is actually happening. It's going to happen because, in the same way as a photon is emitted by a Bremsstrahlung, right? So you have an electron coming along, and then it emits a photon and becomes another electron. It's going to be in a field to do that. But then, at the end of the Big Crunch, the reverse is happening. The photons are going to be absorbed by electrons because you're pushing them all into a very small space. Now, I'm not sure that Albert agrees with that, but
the system is going to be very simple in that sense.
yeah, I mean,
One state or a very small number of states, much smaller than before, and it is like a tendency to simplification of the system, right?
yes, and I suppose that at this Big Bang, Big Crunch event, whether I don't know whether inflation occurred or not, but I see that as being a very simple state, okay, and very simple, like entropy of 0.
Zero, so simplify minimum. Zero.
If time is a loop, then the positive, and I mean, going forward or backwards, becomes meaningless, right?
No.
Yeah, because you can't you can't say this event is later than this event because you can go all the way around. There's no ordering. You've lost the order of earlier and later.
The order is there in the same way that on this table, if you think of space, there's an order in space of things. Here, there's an order in space.
Yes, but time, you've lost the ordering in time.
Not within a local part of the universe.
Not in a small part, but if you take the entire global thing, you've lost the ordering. Just like you cannot. If I
Well,
were,
it's the same as a clock. You could say 2 o'clock's after 1 o'clock.
but it's also before the next.
But I mean, to a normal, there's a meaning to the fact that 2
Yeah,
o'clock.
if you
It's
remember.
nearby, and it's the one
It's nearby.
It's the closest
Right, but you-
path. It's
I mean, my birthday and my birthday. Okay, my birthday is after my birthday, right?
Unless you go-
But when in the very, very far future, the universe has come down to a big crunch, and then it turns into the Big Bang again. That sort of erases everything. And my birthday is still, it's exactly the same. It's not like I'm a different person after you've gone. The whole of space and time is spread out before you. Okay, that's it. The whole of space and time.
Yeah.
You see what I mean?
So there is an error of time still.
Yeah.
But only locally.
The Big Bang, Big Crunch, you are just switching the day, and again you are starting from 0 a.m.
There's
You map
no
it.
end.
You map it. You take whatever. I mean, you can draw anything on a long strip of paper, and you
can't
can
order
join them
points on the
together. And that is the whole of the strip of paper. And you can be an ant crawling on the strip of paper, and you come back. But once you come back, you're in exactly the same state that you were when you started out.
For this you
But also-
definitely need simplification, error of time.
Also, the mapping may be very complicated. Like, let's say we have a complex number theory. Some of them can be multi-layered. So then this recursion cannot be that simple. I mean, let's say if you take a graph of logarithm in a complex space with a logarithm z, so then when you return in at the same angle on this radial angle, you can jump on a very different state because it will be a different layer.
It's logically possible, I think. I mean, that is to say that you could have. We're here. We go to the Big Crunch and then the Big Bang, and after the Big Bang, it is in a different universe. But then you again come back. But you're not going to have an infinite number by fiat. No infinite number.
Mm-hmm.
So I could have, and I started off actually with the idea that we have a bouncing universe, but starting here, going to the Big Crunch, and then again to the Big Crunch, and then identifying points A and C. It's possible. You could have more, but as long as you don't have an infinite number. But I don't see any reason for having more than one, but you could have.
But on the stage, when you when you have entropy decreasing, which you need in your model, entropy increasing and entropy decreasing along this entire circle torus, the stage where entropy is decreasing, probably life is impossible.
Absolutely. It's the end of it.
This is
You're
simplification.
now talking about the whole universe being in a cubic millimeter and then smaller, right? No life there. So the psychological arrow of time's gone. Okay.
So life is possible only at the stage when entropy is increasing.
Actually, yes, I would.
But I mean, entropy can be increasing locally, but it doesn't necessarily mean that it's always, the arrow of time is always the same direction. It can change sign.
But entropy at the beginning of this model, at least as far as I understand it, entropy first increasing, and then at a certain moment entropy starting to decrease.
Well, it could increase and decrease, or it could oscillate, or.
Yeah, but
yes.
I don't see that when the universe is as big as it can be, entropy starts to decrease. As I see it, because when the universe starts to recollapse, nothing's going to change if there's any life there still. But the entropy would decrease only when it's so dense that the final states, the number of final states is going down. So, this is an asymmetry, if you like.
I see. Okay, this is asymmetric.
So I would see the entropy decrease happens in the last.
At the very last moment. Okay.
Yeah, as I see it. Yeah.
But maybe not necessarily. So this is actually an open question. Where,
Yeah.
which moment, say.
I mean, people are even talking at some stage said maybe the arrow of time reverses when the universe starts contracting. I don't see that as being sensible at all, because we're not going to be aware. We're not aware in our daily life of the universe expanding. So why should we be aware of it starting to contract?
When the number of states is starting to decrease, then if any observer is still possible to be
it will
there.
eventually, but that if the universe is decreasing, if you just switch the sign of the expansion now to contraction now, then I don't think we'd see a difference.
Yes, exactly. But entropy will.
But eventually, entropy will go down.
With a cup of tea, we'll still see the entropy.
But
is
locally
decreasing,
it
maybe
will
globally
grow.
it is decreasing.
Yeah.
Locally it will grow. in
Locally
this
it
case.
will grow.
When and where it decreases.
But maybe globally it will start to decrease. Who knows? So maybe we
You can't-
won't be able to realize it.
You can have it
So
locally
certainly,
growing everywhere
the
and
psychological arrow of
decreasing.
time is not going to be there anymore. Right?
Then we call it occasion, I guess.
Psychological, I mean, as I see it, that is because we remember the past, because actually our physical status of our brains changed by the memory.
So the past
And
is
when
happening,
that
the future
occurs,
isn't.
that is an increase in entropy. Sorry. But anyway, this was about topology. Now, the psychological or philosophical question is, okay, I've got this topology of our universe. What, if anything, is outside? Okay. And I don't have to say anything about that, actually, I'm talking about our universe. However, you could say, well, it's embedded in some outer superspace time together with other universes. Or you could say it's embedded in spirit. I don't know, whatever you can put there, because I don't have much to say about that. Personally, my belief is that this is one fluctuation, like a vacuum fluctuation in some outer space time, together with a huge number of others. But that's